Hey guys! Alright, it's me again. Today I'm going to teach you how to do another physics problem. This one's on gravity, and it's from 1994, and it's the third mechanics question. Alright, so I'm going to read you the problem, and then I'll show you the picture, but I drew my own diagram, so it's a lot easier for you guys to see, okay? Alright, a satellite of mass m is in an elliptical orbit around the Earth, which has mass m of e and radius r of e. The orbit varies from closest approach of A to point A to maximum distance of B from the center of the Earth at point B. At point A, the speed of the satellite is v, which is v initial. Assume that the gravitational potential energy, U, is equal to 0 when masses are an infinite distance apart. Express your answers in terms of A, B, ME, RE, V, and G. Okay. For A, they want us to write the appropriate definite integral, including limits, that can be evaluated to show that the potential energy of the satellite when it is a distance r from the center of the Earth is given by UG is going to be equal to negative G ME M over R. Alright, so basically this is the picture. Hold on. There we go. That's the picture. And here, I drew out a bigger one for you guys to see. So first they basically just want us to prove that the formula for the potential energy, which is going to be UG, is going to be equal to negative G, which is the gravitational constant, ME, which is the mass of the Earth, times the mass of whatever the object that's orbiting it, divided by the radius. So basically they want us to prove this formula. Alright? Okay. So first, we know that energy is going to be equal to work, which is also equal to the change in potential energy. Correct? Alright. We also know that work is going to be equal to force times distance. Well, force dotted with distance. But in this case, it's also force times the radius. So, there we go. Alright. So when we take the d and then we take the integral of both sides, we get that. But on this side, because we're taking the integral and then the derivative, we can just cancel those because those cancel each other out. So we're left with the integral of f dot dr is equal to the potential energy. But from earlier, we know that the gravitational force is going to be equal to G times the mass of the Earth times the mass of the object divided by the distance, the separation distance squared. So that is going to be equal to integral of G and E and r squared dr. Right here. But because we know that the gravitational constant is going to be constant, the mass of the Earth is always constant, and the mass of the object that is orbiting is also constant, we can take them out of the integral. So we're going to have U is equal to G, the mass of the Earth, times the mass of the object, times the integral of 1 over r squared dr. We are going to be integrating from infinity to r because we're going from the least potential energy to the greatest. So infinity to r. See? There are our limits of integration. Okay, so the integral of 1 over r squared is going to be equal to negative 1 over r. So G and okay, so using integration, that's exactly what we get. Now we're gonna apply the limits, okay? All right. page. When we apply the limits, it's going to be negative g me times m 1 r. Okay, so when you apply the limits, this is exactly what you get. But we know that 1 over infinity is going to go to 0. There we go. Sorry, that's backwards, so I can't really see. That's an awful circle. But basically, that part goes to 0. So it's just u is going to be equal to negative g times the mass of the Earth times the mass of the object that's orbiting over r. And that's part A. Alright? Now we have to get through F. Alright, next is B. For B, they want us to determine the total energy of the satellite when it is at A. Let's go back and show you point A. Right here. That's point A, alright? Okay. So the total energy is going to be equal to the potential energy at that point plus the kinetic energy at that point. There. Okay. From what we just found in the previous step, we know that the potential energy is going to be equal to negative GME times the mass, but this time it's going to be over A because, as seen here, the distance between the center of the Earth and the point A is equal to little a. So, and we know from before that kinetic energy is equal to 1/2 mv squared, but we're given the initial, so rho, so we just plug that in. And it's we're gonna be using the mass of the object because the object is what is accelerating, or in motion at least. So basically, that is the total energy. Here's the potential, and here's the kinetic, and well, that's part B. Alright, now part C is, what is the magnitude of the angular momentum of the satellite about the center of the Earth when it is at A? Okay, so we know that angular momentum is equal to m times v cross r. There. Okay, so when we want to plug that in, because that's a lot easier for what we're going to be doing, we take the mass of the object, and we're going to use rho because that's the velocity that they gave us. And for the radius, or the separation distance, again, we're going to be using little a because that's the distance between the center of the Earth and point A. So the magnitude of the angular momentum at point A is m rho little a. Alright, we're almost done. Okay, now part D is asking, determine the velocity of the satellite as it passes point B in its orbit. Okay, so for this we're going to use the conservation of angular momentum. So we know that the angular momentum at A has to be equal to the angular momentum at B. Right there. Okay. So we found the angular momentum at A, so we already know that's m rho a. And we're going to set that equal to the angular momentum at B. So it's going to be the same thing, it's just going to be m rho, but this time the separation distance from the center of the Earth to capital B is again little b. So we're going to use that for the radius instead. So basically we have m rho a is equal to m rho b. Now, because it's the same mass at both points, we can cancel those out. And since we want to solve for the velocity at B, we're just going to use algebra and rearrange the variables. So when we're solving for VB, we can divide B from both sides. So VB is going to be equal to rho A over B. And that's going to be the velocity at point B. Alright, on to part E. Okay, Now it says, as the satellite passes point A, a rocket engine on the satellite is fired so that its orbit is changed to a circular orbit of radius A about the center of the Earth. For E, they want us to determine the speed of the satellite for the circular orbit. So now they are taking a circular orbit about Earth. Okay, so they want us to determine the speed of the satellite for the circular orbit. So we know that because it's a circle, well, it's a sphere, the centripetal force is the gravitational force. So centripetal force is going to be equal to the gravitational force, which is going to be G times the mass of the Earth times the mass of the object revolving around it, divided by the separation distance squared. But the centripetal force is also equal to the mass times the velocity squared over the separation distance. Okay, so from that, we are able to cross out both m's because they're constant at both places. And then we are going to solve for the v squared. So basically, when we're solving algebraically, we're going to get v is equal to the square root of g times the mass of the Earth over r. But in this case, r is a because that's the separation distance from the Earth to point A. Okay? Alright, now we're on F, the last part. Okay. Determine the work done by the rocket engine to affect this change. Okay, so in this case, work is going to be equal to the change in kinetic energy. There we go. Alright, so we know that it's going to be, kinetic energy is going to be equal to 1/2 mv final squared minus 1/2 mv initial squared. Okay, because 1/2 and m are constant, we can take them out and just plug in for v. So we have 1/2 m times v final is the v that we had just found, and since it's square, we we take out the radicals. So we're gonna have okay, so that's what we have. And when we solve this out completely, we get the work is equal to 1/2 m times GME over A minus VO squared. Okay, so once you do out the algebra, and since it's a radical, we square, and so that's what you're left with. And they give us VO, so we can keep it in terms of that. And there's the work. Alright, so we finished all 6 parts of this problem, and I really hope that I helped you. If you have any questions, please let me know. Alright, thank you. Have a great day.